Hi everyone, and welcome to the second hints video for your spring break assignment. I was able to end up doing this a little bit faster than I thought I would be able to, so that's why it's going up pretty much the next day after the first one. So let's go to the first problem. This is really starting the second half basically of the packet. So the problems are going to be in the same format as you saw in the first half, where the first two are calculator questions and then the last four are non-calculator questions. So in this first problem, what we have is a can that has a radius of 10 millimeters and is used to measure rainfall in this fictional town called Stormville. Now, what they tell you, and this is a big point, you need to really note this, is that initially the can is empty. Okay, and then rain is going to enter the can during a 60-day period, and the height of the water in the can is modeled by this function S. S is in millimeters, T is in days, and the rate, they give you the rate that the water is rising in the can, and that's this derivative, and it's 2 sine of 0.03 t plus the 1.5. Now, according to the model, part A, according to the model, what is the height of the water in the can? Well, in this case, because this can is initially empty, this is really looking at the total change. What is the displacement, if you will, in terms of the amount of water in the can? And so you can just go through and evaluate that, set that up as a definite integral and evaluate it. Again, this is a calculator problem, so you can put that into your calculator. Make sure you round your answer to 3 decimal places. Now, part B is an interesting question as well, because they want to know what's the average rate of change of the height of the water. Well, the average rate of change, again, we have that formula where the average rate of change is 1 over b minus a times the integral from a to b of f of x dx. That's the average rate of change of any function f over the integral from a to b. Well, if you look at this one, because they're asking for the average rate of change, what is the average rate of change of the height of the water, really what they're looking for is what's the average value of this function right up here. Well, you set that up and you'll notice that the integral portion of this average value function is going to be the same as the integral that you used up here in part A. In the next one, assuming no evaporation occurs, what is the rate of the volume in the can changing at time t equals 7? Well, on that one, remember the volume of the can, a volume of a cylinder is pi r squared h. Well, in this case, the volume function that we're working with, R is fixed at 10 millimeters and H is S. So that's going to be pi times 10 squared times S, or 100 pi times S. So when you take the derivative, again, with respect to time, you can then go through and calculate how the volume is going to be changing. So just take this, V equals 100 pi times S, and calculate, it's basically a related rate. Take the derivative with respect to time, plug 7 in, and you can get your answer there. During the same period, rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. The height of the water in Monsoon can is modeled by the function m, where m is this function. The height m is measured in millimeters, t is measured in days, just the same as what we had. Excuse me. And what we have here, we're going to let d equal m prime minus s prime. Well, you already know what s prime is. You're given s prime. You're told m, so you're going to have to find m prime. Now, they want you to apply the intermediate value theorem to the function to show that there exists a time between 0 and 60 at which the heights of the water of the two cans are changing at the same rate. Notice Please notice here that they did not ask you to find what that time is. They just want you to apply the intermediate value theorem to show that there must be a time where where the two heights are going to be the same, are changing at the same time, at the same rate. So what they're really asking you to do on this one is just show that this function d, that there are times when this function d is positive and times when this function d is negative in the interval from 0 to 60. So just go through and show that, and therefore, again, remember what the intermediate value theorem says, that if at one point the function's value is positive, at another point the function's value is negative, somewhere between those two x coordinates, if this function is going to be continuous and differentiable, somewhere between those two x coordinates, this thing must cross the x-axis. So it would have to be 0. In problem number 2, we have a 12,000 liter tank of water is filled to capacity. So at time t equals 0, the amount of water in the tank is 12,000 liters. Water is going to begin to drain out of the tank, modeled by R of t, and you have the R of t as this piecewise function that you have right here. Part A is R continuous at S. Show your work leading to your answer. You've dealt with this already. We talked about it in the last video. We also talked about this on Thursday before break. So in terms of going through and calculating when that is, if it's continuous at S, that you should be okay with that. Find the average rate at which the water is draining from the tank between time t equals 0 and time t equals 8. Well, again, this one right here is going to be the integral. You're really taking the integral of R of t from 0 to 8, but you have to look at it in two pieces. So you're going to have, you're going to use two definite integrals, one that goes from 0 to 5, and you're integrating that piece, and the other that goes from 5 to 8, integrating this piece, and using the calculator to go through and evaluate those. In part C, find R prime of 3 using correct units. Explain the meaning of in the context of the problem. Well, R prime of 3 means you have to look at which piece you're working with. In this case, you're working with this part up there. You're finding the derivative of that at t equals 3. Now the units part is going to be a big part on this one because this is a calculator problem. You could actually go through and get that value without necessarily going through and doing the derivative. But the units is what's going to make or break this one. You have to remember that in this case, R is measured in liters per hour, and T is going to be measured in hours. So in this case, when you set this up, your units, remember to find your units, you take the units of R divided by the units of T, and then simplify that. So that's what will get you the units there, and then it's explaining what that means in terms of the context. Next one, write but do not solve an equation involving an integral to find the time A when the amount of water in the tank is 9,000 liters. All right, so what you're going to do there, you want to go and evaluate this one. You got to find the time when it's equal to 9,000 liters. So it's going to be, it's really going to happen when you take 12,000 minus the definite integral from 0 to some value x of R of t. Now this one does end the calculator portion of this part of this portion of the AP exam. It's just the first two questions that you get your calculator on. So again, like we said before, it's very important that you go through, identify calculator problems, and do those calculations that you can with those, and save portions that you can do without a calculator for later if necessary. But try to go through and do these calculator parts first. Now we get to the non-calculator portion. In this first question, again, this is very similar to questions we've seen. In fact, different exams have some similarities associated with them. this looks pretty similar to one of the problems that we talked about before on Thursday, I think, with the 2012, but can't remember. In this case, what we have here is f of x equals the square root of x, g of x is 6 minus x, and r is the region bounded by x, the x-axis in the graph. So what we're looking at here is this region right there. First thing I want us to do is find the area of R. Again, on this one, as we talked about on Thursday, you can use either horizontal or vertical slicing. Just remember, if you choose to use the horizontal slicing, because then you would only need one integral. If you choose to use the horizontal slicing, you have to go and solve each of these equations for x. So you have to rewrite them as x equals. Now in part B, this one is going to look very familiar to you because we're taking a region. That region, the base of the solid is in this. This is no longer, we're not doing a rotation. It is just that the cross-sectional faces, when I slice this perpendicular to the y-axis, is a rectangle whose base lies in R and whose height is 2y. Right, but do not evaluate an integral expression to give the volume of that solid. So what they're looking at here, perpendicular to the y-axis, is slices are going like this, and also because of that we are integrating with respect to y. So that means for this particular problem, because it's perpendicular to the y-axis, I definitely have to go and change the two boundary equations to rewrite them as x equals. Now the height is going to be 2 times the y value. Okay, so the base of my rectangle is just this. The height is 2y. So the volume here, or the area formula, is going to be 2y times whatever expression will give you that length right there. And then part C, there's a point P on the graph of f at which the tangent line to the graph of f is perpendicular to the graph of G. Find the coordinates of point P. Well, remember, in this case, G, the slope here for G is -1. So perpendicular lines have slopes that are opposite reciprocals. So really what we're doing on this one is you're just trying to identify the value of x so that the derivative of f of x will be equal to +1, because a +1 slope would be a line with a +1 slope would be perpendicular to g of x. So that's what you just set the derivative of f equal to +1 and solve that for x. In number 4, you're told that f prime of x is 4 minus x times x cubed. Now you have to keep in mind that x is only valid for values of x greater than 0. So the first question, find the x-coordinate of the critical point of f. Well, that's really looking at when the first derivative is 0 or undefined. In this case, a lot of people want to claim 0 because it would be undefined at 0, but 0 is not included, so that cannot be a critical point. So there is only one. It's going to be what makes this thing equal to 0. And then do your analysis to determine if you have a relative max, a relative min, or neither of that function. Next one, they want you to determine the intervals on which the graph of f is concave down. Justify your answer. Remember, to find concavity, what you're really looking at is when the derivative is, the second derivative is what that sign is going to be. So you have a point of inflection where you have possible points of inflection, where the second derivative is 0 or undefined. So you'll have to go through, take the derivative of this, identify where you have possible points of inflection, and then do your analysis to determine the concavity at that point. Now you're only looking for when the graph is concave down. Graph is concave down when that second derivative is negative. And the last one, they want you to determine the function f. When people look at it, you're told f of 1 is 2, so there's your initial condition that can identify c. On this problem, what the mistake that people make often with this one, and I've seen some people do this with these, where you go and say, how am I going to integrate this? Basically, there is no power on the 4 minus x, so you can distribute that x to the negative 3 power inside there. And so when you do that, you're going to get f prime of x equal to 4x to the negative 3 minus x to the negative 2. And now that's just a power rule. So you can go and integrate that. And remember that when you plug once you do find the antiderivative of that, remember your plus c, you know that when you put when you got this initial condition, that f of 1 equals 2, that will help you find c. Now this next problem, number 5 from this set, is a little bit different in terms of what is set up and how you're working with it. You're given a table here, and in your table you have time and then b, which is the distance that we are from the western end of the track. So what's happening is that he has an east-west track, and so he's riding back and forth. So I have this east-west track, okay, and the value of b, here's the west, here's the east end, and the value of b is just the distance that we are from that western end. So he's on this unicycle riding back and forth on there. And so the table gives the values of b, the distance from the western end. It gives the values of v, which is the velocity at certain times. So first up, they want you to go and for part A, just use the data to approximate the acceleration. Well, you're approximating the derivative of the velocity function at t equals 5. Again, this is a problem that we saw on Thursday and also in the last section. So going through and working with that one shouldn't be a problem. Now the next one here is a little bit interesting because of the fact that they want you to go through and explain what this definite integral means. Well, we talked about that in the last video. What that means in the context of the problem, and then approximate this definite integral, that definite integral, using a left Riemann sum with the subintervals that you see in the table. Now, so you're using a left-hand Riemann sum, and you're approximating with that. Now, the issue comes in with the absolute value. You don't really have to worry anything about the absolute value because if you look at all of these, all of our velocities are positive. So it's just really going through and approximating that definite integral for this particular problem using that left-hand Riemann sum. Please remember that, again, as in the previous case where we had to go through, and same thing with what we saw on Thursday, that our changes here are not, they are not constant. We're going up by 10, then up by 30, then up by 20. So it makes a difference on that. And then for the value for t being from 40 to 60, there must be a time t when Ben's velocity is 2 meters per second. They want you to justify your answer. Basically, you're supposed to show that that has to happen. And what really is happening here is really the mean value theorem. If you remember, the mean value theorem says that if a function is continuous and differentiable, then there must be a value between a and b such that the derivative of the function will be equal to the slope of the secant line connecting the points on the curve at x equal a and x equal b. So basically what you just want to go through, use the mean value theorem here to show your justification. A light is directly above the western end of the track. Ben rides so that at time t, the distance lt between Ben and the light surface, light satisfies, this equation, which is a Pythagorean theorem. At what rate is the distance between Ben and the light changing at t equals 40? Well, again, what you have to do on this one is plug in the take the derivative with respect to time. And now you have L of t, that thing squared, equals 12 squared plus B of t, that thing squared. So you do have to use a chain rule to calculate that derivative. And then determine what happens at t equals 40. You know what B is at t equals 40, because that's on your table, and then you got to use that to determine what L would be at t equals 40, and then you're able to go and solve how that is happening, because you already know what B prime of t is at 40 as well, because B prime of t is the velocity at t. So do the chain rule, take the derivative of that as it's written, and then start plugging in the information that you know, and you should be able to solve that one very, very quickly. All right, now this is the last question on here. We have a graph in this problem in number 6 where we have the graph of G. Up here it is piecewise linear, so that just tells me that these are lines, and so that this thing right here is a triangle. And I can evaluate the area of that triangle by just using 1/2 base times height. My base is 6 pi, my height is 2 pi, so the area comes out to be 6 pi squared. Okay, but they want us to, we're defining a function f as being g of x minus the cosine of x over 2. And the first thing they want us to do is find this definite integral. And they want to show the computations that lead to this answer. Well, you know that this here, f of x is equal to this. So one of the things I would do in terms of this problem, I would break that into two integrals. That would be the integral of g of x from negative 2 pi to 4 pi minus the integral of cosine of x over 2 going from negative 2 pi to 4 pi. And take that definite integral there and use that to go and calculate to solve that. Okay, well we've already talked, actually I've mentioned already what that definite integral from negative 2 pi to 4 pi of g of x is going to be. So you're set there, and then you just have to do the antiderivative there and evaluate the definite integral for cosine of x over 2 as well. The next one. Find all values in the open interval from negative 2 pi to 4 pi for which f has a critical point. Remember, f is going to have a critical point where the derivative is 0 or undefined. Okay. Well, first of all, I know when I look at this, don't forget about the fact that we have one critical point is at 0 because g is undefined. G of x is undefined, or the derivative of g of x is going to be undefined at 0 because of the fact that it's a limit. And as you come from the left, the limit here is 1. As you come from the right, the limit is negative 1/2. So the other thing you have to keep in mind as well is you got to identify where it is going to be, where the derivative of f, which is going to be g prime of x minus that cosine, or minus the derivative cosine of x over 2, where that is also going to be equal to 0. So you'll have to do some calculations there to determine when that's equal to 0. And then here h of x is the integral from 0 to 3x of g of t dt, and they want us to find h prime of x. Actually h prime of negative pi over 3. Well, what happens on this one? I know that in this case, when I take, I'm going to have to use the fundamental theorem of calculus, that derivative of an integral form, to go through and find h prime, and then it's a matter of plugging in the values of the value of negative pi over 3 in for x, and determining what happens at that point based on the information that you have in the problem. One thing to remember on this one, remember that that the derivative of the integral form that we are familiar with was that the derivative with respect to x of the integral from a to x of f of t dt was equal to f of x. Okay, well, remember that this worked out because that was x. So if you need to, look back in your book and you can see what happened when this was something other than x, how that changed this result. So with that, this does kind of conclude my some hints on this last set of problems that you have for the spring break assignment. When we come back, I'll see you on Tuesday, and we'll talk about these. We'll talk about some other things, and then following Monday, we will start the exam, and that will take place over the following week, all 3 class periods. So the first class period will be the non-calculator multiple choice. The second class period will be the calculator multiple choice. And then the third class period will be the free response. Now, the free response is going to be the full block. So there won't be any time at all to answer questions there. We'll go over the solutions to that on the following Tuesday. So we are getting close to the exam time, so you should be also working on your own on stuff at this point and getting ready for this. So I hope things are going well. I hope you have enjoyed your break, or you are enjoying your break, and we will see you on Tuesday.